Hello everyone, and welcome to this video short where we are going to review some sorting code in Python and do some time complexity analysis. Specifically, we're going to go line by line through the code and identify the number of computational steps, proportionally speaking, that each line of code is associated with. Given that, we will then derive a step count function so that we can then analyze and upper bound the total step counts associated with the Python code. Specifically, in this example, we are going to look at code for a variation of bubble sort. And in this long drawn out example where we will begin with time complexity analysis and then proceed with identifying ways to improve upon the code, we are then going to end this example with some actual runtime analysis to see if we can identify measurable differences with the actual efficiency of the code. So let's go ahead and get started. All right, so first things, we import some number of tools here, and then we're going to investigate the code associated with our bubble sort variation. Right, so this is inefficient version of bubble sort. As you guys know, with bubble sort, the general idea is that we are going to do a double pass. That is, we're going to have embedded loop structure where we start at one end of the array that we're going to sort, and then we're going to repeatedly swap the least item or the lightest item, like a bubble, right, up to the top or the beginning of the list. Right. After that item gets into place, we will then start again at the end of the list and then grab the second lightest item or the least item and bubble that up to the second spot in the list, and on and on and on. So we will repeat this process until the entire list is sorted. The code to do this is identified here, and in the comments you can see that I've specified the number of computational steps, proportionally speaking, associated with each line of code. So for example, in this first line of code, we have a call to a function length where we retrieve the length of the associated array. It is then assigned to variable n. Right? Now this particular line of code here will have some constant number of steps associated with it. Right? Given how the runtime environment keeps track of the attribute of length for each of the arrays, this should be a simple retrieval. And then the assignment operator is also a simple operation for the runtime environment. So a constant number of steps for each of these. So in total, we have a constant number of computational steps. What do I mean by constant number? I mean that the number of steps that are going to be needed to execute this line of code is not going to vary with respect to the size of the input, n. Going to the next line of code here, we see that we have a looping structure that is going to vary based on the size of n. Right? So we are not going to have a constant number of computational steps associated with this line of code. Instead, it will be variable. Here we can see that the looping structure is going to range over the index set from 0 to n-1, or n number of iterations. So here we are going to identify, that the number of computational steps here is going to be the constant number of steps associated with setting up the iteration for each epoch or each iteration, times n, the number of iterations. So here we're going to have a linear number of computational steps, simply C2 times n. In the second looping structure here, right, again, we're going to have a constant number of computational steps associated with the infrastructure of the loop. And then each iteration is going to be n-1, repeated n-1 times. Now note that this line of code is embedded in this looping structure. So this line of code itself is going to be some constant number of computational steps times n-1, or linear. However, that's also going to be repeated n times. So we're going to have approximately n times n-1 computational steps. So a quadratic number of computational steps associated with this line of code. Right, the same can be said for this line of code here, our conditional check, where we're checking to see whether we're going to make the bubble swap or not. Right, now inside of this conditional, the number of times these lines of code are going to execute is going to be variable based upon this condition here. This breaks down into all the different cases we have. So in complexity analysis, we have best case, worst case, and then all of the cases in between. where we identify best case as being the case where we have minimum number of computational steps, and worst case being the case where we have maximum number of computational steps. Right? So the worst case within this context is when we would enter this condition the maximum number of times, meaning this condition here is true, maximum number of times. Right? So if this is true maximum number of times, let's say that we enter this condition every single iteration, then we're going to have approximately quadratic number of computational steps here as well. In order to count up the total number of computational steps, we just simply sum each of these expressions here associated with each line. Right? Thus, we have a time step function t of n, which is equal to the expression noted here. Note that this is overall a quadratic form or a quadratic expression. Right? We can simplify terms to some degree, and I'll leave it in this format here for comparison later on. But note here that we do have a quadratic term. One thing to inspect here before we segue to the second part of our example is that we have this double looping structure where we iterate essentially twice over the entire list. However, in bubble sort, once we bubble up the lightest and then the second lightest and then the third lightest item in the list, those items are in the correct place, and we don't need to iterate all the way to the end or the beginning of the list during each of those inner epochs or those inner iterations. Therefore, we can improve upon this iteration scheme as we have some unnecessary iteration. So in our next example, we're going to dive back into this code, see where we can make some improvements, and then do our time complexity analysis to see theoretically how much of a gain we should get with respect to the efficiency of our improvements. And then we will do some actual empirical analysis. We'll run some trials in Python, time the results, and see if we get some measurable efficiency gained. All right, well, thanks for joining me in this video short, and I will see you in the next one.